In physics, another important property of objects is where their center of mass is, and that's frequently introduced as sort of a tipping point argument, where if we balanced a large mass and a small mass, there should be some place where if we put these on a teeter-totter or on a board, where there'd be a perfect balance between the two elements. And notice it matters where we put that tipping point, where that balance point occurs. We tend to put it closer to large masses and further away from smaller masses. What's interesting is no matter where we define our x coordinates, what turns out to matter when we digest the total formula is simply the location, the x coordinate of a mass, and how large it is. So x times the actual mass of an object. And what we do to get the center of mass, this x bar, is we calculate the sum of where the mass is times its size, and we divide by this expression on the bottom, which is essentially the total mass of all the objects. Sometimes this expression here is called the moment. We won't use that nomenclature here, but you might hear it in a physics class. Another way to think about this, if it helps, is this is essentially a weighted average. We take a total of the masses in both of these, but in the top expression, we actually weigh it, which is an odd phrase to use when we're talking about masses, but we weigh it by the location. So if one's further out, that contributes more in this value to the center of mass location. Also, if a mass is larger, it contributes more to the center of mass in the calculation. Let's work through an example of this to make it more concrete. Here we have a mother and daughter sitting on opposite ends of a 3-meter seesaw or teeter-totter. So we know we can define the two endpoints here as x equals 0 and x equals 3. The mother has a mass of 60 kilograms, the daughter weighs 20 kilograms. How close to the mother's end would the support need to be put so the two would be in perfect balance? So again, we imagine, because there's a heavier mass at this end, that somewhere on this end of the beam would be the perfect tipping point to keep these two elements in balance. Well, that is exactly what we're asking for in terms of the center of mass. And so we can take our ingredients here, and let's call it x1 is the mother's position, that would be 0. And mass 1 is 60 kilograms. At the other end, the daughter can be described by an x location as well. Let's call her mass 2. She's at location 3 meters, and the mass there is 20 kilograms. Filling in the blanks for our center of mass calculation then, we want the sum of the x times the masses, so 0 times 60, plus 3 times 20. And all of that over the total mass, 60 and 20, added together. Now it might feel that somehow the mother's mass is not being considered in this because the 0 multiplier is there, but because she also appears in the denominator in the calculations, that's going to have a net effect on the center of mass, and we'll see how that plays out. Calculation-wise, we end up with 60 over 80, or 0.75, and this is a center of mass. You can check the units yourself, but that's going to be in meters. It's a distance. And specifically, that distance is 3/4 of a meter along this seesaw. So if we put the center of mass there, that would be a perfect tipping point to keep the mother and daughter balanced on this beam. So that question's a pretty traditional early physics question. What we want to be able to do is handle a different kind of scenario where the mass is spread out in a continuous way. To give us a concrete example, let's look at an example from earlier in the course where we had a 2-meter long rod where the density was changing. It became more dense as we moved from left to right. This rod would also have a tipping point somewhere, or a perfect balance point. Take a moment to think about that and ask yourself, where would the center of mass or that tipping point on the rod be, given what we know about the density and the length? Pause the video for a moment, and then we'll check in. All right. The key thing here is that the density is increasing, and so there's more weight at this end of the rod than there is at the beginning of it. And what that points to, if it's heavier on the right, we're going to need to move the tipping point a little bit to the right of 1 to balance that out. We'll have less mass down here, but it's going to move further away from the center, and so that's going to make it balance out with the heavier mass on the right-hand side. But how do we determine exactly where that is? Well, that's going to be the process we used from before of slicing up the total mass and seeing how it applies to the center of mass calculations. If we have discrete masses, we can use the formula that's written up here. However, there's no reason at all why we can't take this same picture and talk about a slice delta x wide at a position x and talk about the mass of that slice. And if we take the mass of that slice, add it up times its position, or just add it up by itself, and we accumulate that over the total length of the rod, we'll be able to fill in all the blanks for our center of mass calculation, even though we have something continuous. And all we need to do to accomplish that is turn our sum into an integral. The x is literally the x location of our slice. The mass is where we get some of the ingredients from earlier. We have the density, 3 plus 0.5 x's, times the width, delta x here, or if we're writing it in integral terms, we can go straight to dx, and then divide that by, instead of adding up total masses, we're going to integrate total masses, or the mass of our slices, times dx. Put the last finishing touches on the integral, and then we'll go back and check the units. In the original scenario, we had meters distance, and we had kilograms for our masses, and we divided by kilograms. When we cancel all that out, we end up with meters. The same thing is happening here. We have meters on top, and then these two terms together, one is kilograms per meter, and the other one is in meters as well, meters of length. And so those two cancel, and we get kilograms times position, kilograms times distances, or the same units as we started with a discrete sum. Same thing applies in the denominator. We're adding up kilograms times little units of length, and that gives us units of mass in the denominator as well, as we would have had with the discrete term. So with a clever observation about the mass, instead of calling it the mass of this whole thing, we call it the mass of a little slice, and then we add up all those little slices using an integral. We can easily convert from discrete to continuous kinds of calculations. All right, so where does that leave us? It leaves us ready to evaluate these integrals. Now notice here we actually have two separate ones. You can do them literally separately. Here they're simple enough that we'll keep them together. In the first scenario, we should expand out the product, the x, into these interior terms just to make it easier to integrate. So the integral from 0 to 2 of 3x plus 0.5x squared all over the integral of 3 plus 0.5x. And notice the integral is essentially a parentheses. We can't cancel these terms top and bottom. We have to do the integral first, and then if something cancels, we can do that afterwards. But you can't just go around canceling that and canceling that. If you could, life would be a lot easier, but it also would not give you the right answer. So we evaluate these two integrals separately. Here we'll have 3x squared over 2 plus 0.5x cubed over 3. All of that evaluated between 0 and 2. Then we have the denominator. That'll be 3x plus 0.5x squared over 2 between 2 and 0. Subbing values in, we're going to have 12 over 2, that'll be 6, plus 8/3 times a half, that'll be 4/3. And in the denominator, we'll have 6 plus 4 over 2 is 2 times that. That's another 1. In fact, this is a value we found earlier. This was the total mass of this rod of 7 kilograms. And then we have this new expression on the top. When we compute all this out, we end up with a value of 1.0476 meters. What does that indicate to us? It means that out of our 2 meter length, the center of mass is moved just slightly to the right to 1.047 meters. That would be the tipping point or the balance point for this rod.